What is heat load in quantum computer cryogenic systems? Imagine trying to keep a delicate snowflake from melting in the middle of a desert. That's similar to what scientists do when they keep quantum computers at ultra-low temperatures. These systems need to stay below 15 millikelvin, which is just a tiny fraction above absolute zero. To do this, they use special cooling machines called dilution refrigerators. But maintaining such cold temperatures isn't simple. It requires managing the heat that naturally tries to creep into the system. Heat load is the total amount of heat energy that must be removed from the cryogenic system to keep everything cold. It's like trying to keep an ice cube frozen in a warm room. Even small amounts of heat can cause problems. In quantum computers, especially those using superconducting qubits, heat can cause the qubits to lose their quantum state, a problem called decoherence. This makes calculations less accurate and can even cause errors. Sources of heat in these systems come from many places. Wiring that connects the quantum chip to outside electronics conducts heat inward. Control and readout electronics, like amplifiers, generate heat when they operate. Vibrations and thermal radiation from the surroundings also add to the heat load. Active components such as cryogenic amplifiers or control circuits, which are necessary for reading and controlling qubits, produce heat even at low temperatures. Managing this heat load is vital. Engineers use special materials with low thermal conductivity, like stainless steel or fiberglass, for wiring and supports. These materials help limit heat transfer from warmer areas to the coldest parts. They also use thermal anchoring, which means connecting wires to intermediate temperature stages to slowly dissipate heat. This prevents sudden temperature jumps that could disturb the qubits. Another technique involves designing cryogenic electronics that generate minimal heat. For example, advanced cryogenic amplifiers are built to produce near-zero heat. Reducing the number and thickness of cables entering the cryogenic chamber also helps. Every cable and component adds to the heat load, so keeping them minimal is key. The cooling systems themselves are multi-stage devices. They use a series of cooling steps, starting from room temperature and gradually reaching millikelvin levels. Each stage handles part of the heat load, ensuring the system stays cold enough for quantum operations. If the heat load isn't managed well, the temperature can rise, causing the qubits to decohere faster and reducing the system's overall performance. As quantum computers grow larger and more complex, controlling heat load becomes even more important. Without proper management, the system could become too warm for the qubits to function properly. That's why scientists and engineers focus so much on reducing heat transfer, designing efficient cooling stages, and using materials that help keep everything cold. It's a constant balancing act, but one that's essential for making quantum computing practical and reliable.